Hello everyone, welcome to the video solution for physics. This is Edexcel IAL, summer 2018, unit 1, part 3. So let's start. Question number 17. A student determined the Young modulus of a material in the form of a wire using the equipment shown. A control wire with the constant load was used to comparison for measuring the extension of the wire under test. So this is the diagram. So this one is the control wire under test, micrometer screw gauge is used here. So every time a known weight was added to the applied load, the micrometer was adjusted until the spirit level was horizontal. The movement of the applied load was the same as the movement of the micrometer. So list any additional measurements that are required for the students to determine a value for the Young modulus for the material. So in this experiment we are measuring force applied here, and the micrometer is going to give us the extension, but for Young modulus we need two more additional measurement, which is the length and the area of cross section. So diameter and the original length. So for area we need a diameter. So these are the two additional measurements. Part B, a student plotted a graph of the applied load against the extension of the wire. Sketch the graph that you would expect the students to obtain. Of course, this is force extension graph, Young modulus, so it is a straight line passing through origin. Explain how the student can use the graph to determine the Young modulus of the material. So because the students is investigating the effect of load and the extension, so from the graph you can say the student is going to measure the gradient first. The gradient is load upon extension, so F upon delta L. This would be the gradient from the graph, and then you know that the Young modulus is force upon area or stress over strain. That means force divided by area over delta L over L. This is extension. If you simplify this, so Young modulus would be equal to FL divided by A delta L. Clearly you can see that this F delta L is gradient. That means Young modulus can be found by multiplying the product of gradient with length by area. That's how a student can use the data to find or to figure out the Young modulus. A simpler method to determine a Young modulus of a material in the form of a wire is shown. The position of the marker along a meter rule is recorded each time applied load is increased. So this is the equipment marker. Explain two advantages of using the first method rather than second method to determine the Young modulus. Of course, in the second method we are using meter rule to measure the extension, but in the first method we use micrometer screw gauge to find the extension, which will give a more accurate reading than the second one. And also in the first method weight is hung directly on the string, but due to pulley we have some reduced tension. That's why the method 1 is much better than method 2. That's how you can write. The flow of a blood around a body is mostly laminar. The speed of the blood in the body is greatest on leaving the heart, and at a point turbulent flow can occur. Add a diagram to show laminar flow and the turbulent flow. A most typical question, drawing laminar and turbulent flow. So laminar are the flow in which the streamlines or the layers remains parallel. So you just continue with the help of the ruler. You continue and you can say this is the laminar flow, something like this, and if you wish you can add arrow, is fine. So these are the laminar flow. And the turbulent mean when the layer mix and the ADs are formed, so something like that. Okay, so part B. A student wishes to estimate the power output P of the heart. He argues that the heart has to pump out blood at a speed V and raise it to the height h above the heart. He proposed that the following equation for P is equal to 1 upon 2 rho q V square plus rho q GH, where Q is the volume of blood passing a point per second and rho is the density of the blood. Derive this equation for P using principle of conservation of energy. This is the key. Principle of conservation of energy. Generally, if some object or particle is moving, we have two types of energy. One is kinetic energy, and the other one is potential energy. So, or you can say gravitational potential energy, and the total energy is sum of these two. So here you can start your derivation, since the total energy ET is equal to kinetic energy EK plus potential energy or a gravitational potential energy EG or EGPE, and this total energy you can write as power into time is equal to half mv square is equal to it's not is equal to, I'm sorry, this is plus mgh, because we need to find the equation for power. That means just get rid of this time, meaning divide the whole equation by time. So the new equation becomes P is equal to half of m v square by t plus mgh by t. But we know that mass is the product of density and the volume. You know that the density rho is mass over volume. So mass equal to density times volume. So I can rewrite this equation as P equal half m. M is rho into V square divided by T plus m is rho V GH by T. Remember, there is a difference between this V and this V. This is the velocity square and this is the volume. And as per given condition, you see that Q is the volume passing per second. That means Q is in fact V by T, volume per unit time. So you can replace this V by T and this V by T with the Q. So your final equation becomes P is equal to half of rho Q V square plus rho Q GH. This is your required equation. So you can say that you can write this whole equation like this: P is equal to half rho V by T, meaning Q V square, plus rho V by T Q GH. This is your required condition equation. Okay. Question number 2, part 2. Calculate the power output P of the heart when pumping blood to height of 0.4 meter above the heart. Assume that the speed of the blood has not changed since leaving the heart. So it's not that difficult. It's a straightforward question because height is given, densities Q and V's are given. So you just need to plug in all the values in the above formula, which was P is equal to half of rho Q V square plus rho Q GH. So everything is given. Just replace the value. The only point you need to take care of is this Q. Q is given in centimeter cube per second, so need to convert this centimeter cube into meter cube. So you convert this centimeter cube into meter cube and then plug in the value. If you do that, then power output would be around 0.42 watt. Just try it and see if you get this answer. Okay, part 3. Suggest why in practice P will have to be greater than the value calculated in B2. Yes, indeed, the actual value of P should be greater than the calculated value because we did not consider the friction or the resistive force in flow. In reality, when blood flows through the vein, we have a resistive force or friction force between the blood and the wall of the vein. That means blood has to do some work against this resistive force, so P should be greater than the calculated one. Question number 19. An underwater system for detecting earthquake is placed on the seabed. The system includes a pressure sensor and 10 glass spheres. The system is connected to a detachable anchor. Regular signals are sent via satellite to a central control station. Okay, so connecting chain, glass spheres, 1, 2, 3, 4, 5. Okay, pressure sensor, anchor, seabed. The system and the anchor are released just below the surface of the sea. They accelerate for a few seconds and then fall to the seabed at a constant velocity. Calculate initial acceleration of the system and the anchor. So as soon as you just release the system just below the surface, that means at that moment for the whole system, if I consider this system as one particle, after release only two forces are acting. One is the weight and the second one is the upthrust initially. So the resultant force or the net force would be difference of these two. So you can say that F is equal to W minus U, and F is MA equal to W minus U. Upthrust is 2500 Newton and the mass of the system is 470 kg. So you can say that W is mass of the system, 470 times 9.81 minus upthrust 2500. So you can find acceleration after replacing this m with 470, and if you do that, the initial acceleration you will find 4.5 ms minus 2. This is the acceleration. Part 2, explain why after a few seconds the system and the anchor falls to the seabed at a constant velocity. Same reason, a most typical question of a fluid. Initially, weight is greater than upthrust. Initially, weight is greater than upthrust, so we have net force acting downward, due to which initially the system is accelerating, but as it starts falling down due to increase in the velocity along with the weight, and it's not W minus W, I'm sorry, it's U. So now as the system starts falling down, along with the weight and the upthrust, an additional force starts acting, which is the drag force start acting upward, and this drag force D starts increasing with the speed, and the time comes, and this is not W, this is U, sorry. So when the time comes when D plus U equals the weight, then the net force becomes 0, and then object start falling with the constant velocity. Calculate the drag force acting on the system and anchor as they fall at a constant velocity. So drag force. So drag force is D plus U equal to W, because it's falling with a constant velocity. So drag is W minus U. So W is 470 times 9.81 minus 2500. So drag force would be equal to 2110.7 Newton. This is the drag force. B, the system is refloated every 2 years so that the batteries can be replaced. To refloat the system, the anchor is detached from the system, and the glass spheres cause the system to rise the surface of the water, leaving the anchor behind. The total upthrust on the system due to 10 glass spheres is 2500 Newton. It can be assumed that the upthrust on the rest of the system is negligible. Calculate the diameter of one glass sphere. So you can say that, and the density of the seawater is this. Okay, so this is the total force or upthrust due to 10 glass, and if you divide this upthrust with the 10, that means 2500 divided by 10 will give you upthrust due to 1 glass, that means 250 Newton. And upthrust is weight of the fluid or water which is displaced by the single bulb. So you can say that upthrust is equal to mass of the water into G. That means mass of it's a fluid or maybe a water, just because water and a fluid same. So this is mass of the water. So mass of the, it's better to replace W, I'm sorry about that. So mass of the water is equal to upthrust divided by G. That means MW is equal to 250 divided by 9.81 is 25.5 kg, and then volume of the water is 25. So because the density is mass over volume, so volume is mass over density, so mass is 25.5 divided by density, and density is 10 0.30 given here. So you can figure out volume of the water which is displaced by one bulb, and the volume is 0.025 meter cube. This is the volume, and you know the volume of the water is, because this is a sphere, so you can say that 4/3 pi r cube, or d by 2 whole cube, is equal to 0.025. And now clearly you can simplify this equation for d, and you can determine the diameter. So you can take the cube, simplify the equation, make d as a subject. Finally d would be equal to 0.362 meter. That's how you figure out the diameter of one bulb. C was when selecting the material for a connecting chain, all the forces that act on the chain are considered. Explain why the connecting chain should be made of a high strength material. Clearly, because the chain is experiencing many types of forces. Weight is pulling chain down, and upthrust is pulling chain up. So the chain should be made of a high strength material in order not to break the chain due to these forces. And suggest what causes an additional force on connecting chain when the system is on the seabed, because it is in the, under sea, and water is in motion. So due to motion of the water, movement of the water, chain is also experiencing some additional force due to motion of the water. Thank you very much for this video. Have a nice time.